this and the next video, we will take a closer look at one of the most popular types of difference in difference design, namely the staggered adoption design. Some of the insights we will talk about here will also apply to designs where some units are treated and they're all treated at the same time and other units are not. But in many cases, we have difference in difference designs whereby some units, be it people, be it states, be it firms, are treated earlier than others. And you even have designs where everyone in the sample is treated eventually, but the treatment timing differs between those different units. And this is very popular, and the typical way researchers go about this is they estimate a given two-way fixed effect model that has become standard in the literature, and they interpret the results as if they were running a 2x2 Card-Kruger type difference in difference model. And for quite a while, researchers have viewed this interpretation with quite some unease, but somehow we lacked the insights from a methods paper to really clarify what's going on here, like where the difference between the two lies. So to think a bit more carefully about why is there a difference, it's very simple. In a 2x2 difference in difference model, it's very clear what you compare with what. Yet you compare the outcomes of one types of units that have not been treated to those outcomes of a unit that has been treated before versus after. And in a staggered adoption design, or in a design where some units get treated early, other units are getting treated later, here's the challenge. If you see if you see a presenter who presents a paper that uses that design, just ask them, well, what do you compare with what? And you will see that they tell you all sorts of intuitive things. They will say, well, I'm comparing those that are treated later to those who have been treated earlier, or those who have been treated early to those who have not yet been treated. But as I will show you in this and the next video, these interpretations are typically wrong. And there's only recent papers who have shown us why they are wrong and how we can make them right and how we can make them work. So let's jump into that. The starting point here is the canonical two-way fixed effect regression. Okay, so we have here unit and time fixed effects. And then again, we have that treatment dummy. That is one if a unit is in a treated group after the group has been treated. So it's essentially just an indicator for whether the period in which you observe that unit is actually after the unit has been treated. So that's and then you have the textbook difference in difference. With textbook, we mean, Card-Kruger type difference in difference. Units that are getting treated, they get treated at the same time. But then in many cases, that's not the case, because we have many treatments that are rolled out across states, for example. There are some progressive states that start with a policy and then other states follow suit. And if that's the case, then interpreting this coefficient beta here as a difference in differences is getting a lot harder, because we no longer can say what do we compare with what, right? So if all units that are getting treated at the same time, then that's still similar to the 2x2 case. Right? But if you have a rollout and you exploit that some places are getting treated at a different time than others, that comparison no longer works. And so therefore we need to take a close look at what we're doing. But one thing you should not do is you should not interpret any such estimates as the average treatment effect on the treated. Now, if you challenge someone in a seminar and say, well, you're not getting the average treatment effect on the treated, they may say, well, in my literature, there is no such thing as the average treatment effect. And then you ask them, well, what effect do you want? And well, guess what? It just has a different name. Okay, so they want to know what is the effect of treatment on a unit relative to a counterfactual where that unit is not treated, which by definition is the average treatment effect on the treated. But with that estimator, with the two-way fixed effect staggered adoption, you do not get the average treatment effect on the treated, not without extremely strong and unrealistic assumptions. You get something else that you may be able to work with, and what that something else is, we will see. Right? But there are a good few papers that have all come up. You see the dates at which they were published, and quite some of them are still in working paper stages, and they are in the publication process as I'm recording this video. Right? But they have been discussed a lot in the profession because they provide very important insights. And they show that there are two key problems here. One, and this goes for all of econometrics that you're doing, whatever comes out of your statistical software is a weighted average, right? It's an estimator works like a funnel. You put the data in at the top and it condenses the data into one or two numbers, or maybe a couple of numbers, right? And that number that comes out, that's the estimate, that's a weighted average across all your data points. The problem is, well, for us, understanding what an average is easy, but understanding those weights is really hard. And in that case, we actually have a very, very strange weighted average, as in those weights are not intuitive, and those weights mean that we get an effect that is very far away from anything that would be interesting from a policy perspective. And that is obviously quite worrying. The second issue is, and that's somewhat related, is that in many cases, the treatment effects when a unit is treated can vary. So it varies over time. You know, a unit when it's treated and then a year after you see hardly any difference, but maybe the treatment effect will only kick in after several years. And also that some units, when they're getting treated, react more strongly than others. And you can see where the problem lies then in a staggered adoption design, because you're now in a world where, let's say, if those for whom the treatment is most beneficial adopt it first, and the treatment pushes them on a different time path even, then those units that have been treated early might actually be part of the control group for the later treated units. And so you get a weighted average over units that have been treated earlier and later, and that were pushed by the treatment onto a different time path, or that differ in the size of the treatment effect. And that all comes into that weighted average. And then that weighted average becomes really, really hard to interpret. But thankfully, there is people out there who are very, very smart and who offer quite some insight there. And one person whose paper has made a big splash is Andrew Goodman Bacon. So he has proposed what has since been labeled the Bacon decomposition. So this is basically, this paper could have also just been called How the Diff in Diff Sausage is Made. Okay, so he really looks into the ingredients that go into this very simple parameter beta. And the huge achievement of that paper is that he breaks down the weights that go into beta, and he draws a comparison to the diff in diff that we're actually used to, which is the 2 by 2. So what he shows actually is that the beta coefficient that you're getting when you run this standard diff model is nothing more than a weighted average of different 2x2 comparisons. Okay, so what are those? We will look into detail into those, but they are, early versus late adopters, untreated versus late adopters, untreated versus early adopters. These are all 2x2 comparisons. And if you have staggered adoption over many years, this year 2 states, next year 3 states, the next year 1 state, and so on, you may have a lot of different 2x2 comparisons that your estimator simply is a weighted average over. And given that, so we have strange weights over many 2x2 comparisons, that obviously makes the estimator hard to interpret. And also, it's very hard to then get the effect we actually want, that is policy relevant, that is the average treatment effect on the treated. Right? So if I give those states that were treated, what is the actual contribution that the treatment has made? And it's very hard to answer that question from those estimates. Not impossible, but hard. Now, let's look at a simplified version of the staggered adoption design. So here we only have 3 groups. So we have one group that has the subscript U that never gets treated. Okay? So its outcome just moves on a given path over time. Then you have one unit that's here labeled as with a superscript K. It's a bit hard to see here, but it's K. This is a unit that gets treated early. Okay? So that unit gets treated at that time, and then the outcome jumps to a new level. And then you have a third group that is a late treated group that is treated at that point, and then its outcome jumps as well. Now, obviously, in a setting where you have gradual rollout of a policy across multiple units, you could have more than 2 units that get treated at different times. But that is, these 3 groups are the minimum you need to show where the problem lies. Right? But the typical example is that you have actually even more groups. And here I will show you now those 2x2 comparisons that you can make from them in detail in the next couple of slides. But notice here also, so far in formulating the problem, we are in a world where the treatment only leads to a level shift in the outcome. Leads to a level shift. We will later also talk about the problem of the treatment potentially leading to a difference in trend. And if that's the case, bad things happen. Okay? But let's start simple. So what Goodman-Bacon shows in his work is that the estimate beta that you get is a weighted average over those 2x2 comparison groups. And if you have non-treated and then 2 treatment groups, you have 4 2x2 comparisons. 3 of those are those that people always have in mind, or typically have in mind, when interpreting their results. But there is a 4th one that messes everything up. That messes up the interpretation, that messes up the estimation of a policy relevant parameter, and that we cannot without using different methods, it's a problem that we cannot solve. But that is inherent. So if I bet if you have run such an analysis before, that problem is also there in yours and in mine. Okay? It's just there. It's a mathematical problem that comes from the way this estimator is constructed, and comes from the way a 2-way fixed effect estimator works. There's nothing that you've done wrong in the application. You've applied the estimator correctly. It's just the estimator doesn't give you the parameter or the combination of parameters that you actually claim it does, typically. So let's look at those 2x2 comparisons in turn. So the first one is one of the very intuitive ones. Okay, so it compares the non-treated to the earlier treated. And then you get the standard diff and diff, nothing special. The second one does the exact same thing, right? So it's the 2x2 comparison. You compare the non-treated to the later treated, and then the difference is simply, the difference in differences gives you the size of that treatment effect. So basically of that gap here. Okay, so these two are clear. The third one is also intuitive, right? So here now notice that the sample period would go up to here somewhere, but we have cut off the last bit. Why? Well, because here we compare, and it's not we compare this by deliberately choosing things. No, our estimator does that comparison for us. Right? We just never knew about it. Now we know. So here we consider the comparison between the early treated and the late treated before the late treated has actually been treated. Okay, so imagine, Pennsylvania and New Jersey both eventually introduce a minimum wage, just New Jersey is earlier. Then what we do is we simply compare New Jersey to Pennsylvania before Pennsylvania has introduced the minimum wage as well. Okay, and that is also an intuitive 2x2 comparison. And that when you ask people, well, what do you think your diff and diff estimator actually compares here? That's the answer you're very often getting. It's the effect of the treatment on those states that have been treated relative to those who have not yet been treated. Okay, so the control group are those states that have not yet been treated. And that plays a role here, but it's only part of it. Okay, so now this is the third of the comparisons. And now comes the fourth, and that's the tricky one. Because there is also, without people often realizing it, another comparison in there. And that's the one that messes things up. And that's, you compare the late versus the early adopters. So the early adopters are actually here a control group for the late adopters. So here the sample period, the first part of the sample period, we don't need to consider here because there is no variation because none of those have been treated. But then in this middle here, the early adopters have already been treated and are already at that next level. And the late adopters have not yet been treated. But the early adopters are a control group for the late adopters. Again, you could say, well, maybe my estimator doesn't do that because I've never told it to do so, but it does, unless you use a different method. Okay, and that is this comparison is what makes our life so hard. So you have your diff and diff estimator that you get by running the two-way fixed effect model is a weighted average over comparison of the different types of treated units to the untreated units, as well as when you take any two units that have been treated at a different time, in some parts of the sample, the early adopters are a control group for the late adopters. That's what you see here. And in other parts of the sample, the late adopters are a control for the early adopters. Okay? And so that already makes it very hard to interpret, even if the weights for each of those may be straightforward. And surprise, surprise, the weights that over which the weighted average is then computed are also not exactly trivial. So let's look into those. Weights a little bit. So here is the decomposition theorem from Goodman-Bacon, which basically tells us the following: the difference in difference estimator that we get from this two-way fixed effect model is a weighted average over those 2 by 2 pairs. And so here you have the treated versus the untreated. And here you have the late adopters being a control for the early adopters. And here you have the early adopters being a control for the late adopters. And so then those so you have those 4 groups in there, and then you have the weights. Okay, so the first set of weights are the weights in that estimator for the clean diff and diff comparisons, untreated versus treated. And the second set of weights are those for basically the portion of the estimator that is due to the staggering in the adoption. And then you have a third set of weights that among those that exploit the staggered adoption, early being a control group for the late, late being a control group for the early, what the relative weight of these type of comparisons is. Can you influence those as a researcher? No. They are automatically, these weights follow from you using a two-way fixed effects estimator. So, what are those weights? And now this is where things get really tricky. Right? So the first thing we should look at is we should look at the overall variance in the treatment. Right? So the overall variance in the treatment here is not the pure variance of a dummy variable because it already difference out those fixed effects. Right? So it's the variation of the treatment dummy after conditioning on state or unit and time fixed effect. So it's basically the within group variance. So the weights then, let's look first at the first 2 weights because these are the really important ones. They depend on 2 different factors. The one factor is one that is intuitive, which is it's the relative sample size. Okay, so what is the relative sample size of that 2 by 2 pair relative to the overall sample? And obviously, if that 2 by 2 pair, there is only very few, let's say, late treated units and many untreated units, then obviously that, or let's say there is very few untreated units and very few late treated units, but many early treated units, then obviously the late versus untreated would have a very small relative size within the overall sample. Okay? So that's sort of intuitive, right? So if the comparison, that 2 by 2 group is big, it gets a bigger weight in the estimator. But where things become really tricky is that you have also part of the weights is simply the variance in the treatment. And that, when you think about it, should not surprise us because any fixed effect estimator is a variance weighted average, right? So you have the fixed effects define groups, and then your fixed effect estimator weights all the observations by the within group variance in the treatment. So if there is a lot of variation in the treatment within a group, it gets a high weight. If there is not much variation in the treatment, it gets a low weight. The question is just, when do you have a lot of variation in the treatment in these groups? Okay? And there are a couple of dimensions that we need to think about here. So if you think about a 2 by 2 comparison here, right? Let's think about it in terms of a table. Let's say here you have group K and here you have group U. U stands for untreated. And then let's say you have at some point treatment period T star, and so you have zeros before that, and then you have ones in the treatment indicator, and then you have here zeros all along. Yeah? that group has a different variation in treatment relative to, for example, a group where the treatment happens at the very start, so maybe in the second period, right? And so you have zeros here. So clearly, and if we maybe change the thing up here and have the treatment maybe right in the middle, then clearly the first group up at the top has a greater variation in the treatment than the second group. Yeah? And we will also show this with a numerical example, that if a group is treated in the middle of the sample period, that 2x2 comparison with that group versus another group gets a larger weight in the estimator than a group that gets treated at the start or at the end. And that's really hard to swallow, because if you want to have a policy relevant effect that could be the average effect of a place getting treated, then you don't want to have a situation where the effect that you're getting is mainly driven by those treated in the middle and not at all by those being treated at the end or at the beginning. That is no problem if the treatment effects are the same, right? So if the early adopters and the late adopters and those in the middle always have the same treatment effects, then it doesn't really matter. But suppose if the treatment effect is much higher for those that get treated early and very low for anyone getting treated a little bit later. What happens then is that you vastly underestimate your effect, because the units in the middle for which the treatment is hardly effective actually have a huge weight in your estimator. And it's not because you want it to have a huge weight, but simply for mechanical reasons that's the case. So that's something to be aware of, that's happening. So you have those strange 2x2 comparisons. So early adopters are actually a control group for the late adopters. And so there is an additional layer of those weights. That is basically what share of time the early adopters have spent on the treatment and the late adopters haven't yet. Right? That's what basically this weight here tells us. So that doesn't look simple and transparent and trivial at all. And it's in sharp contrast to the general perception that diff in diff is just, you run your two-way fixed effect model, you have your staggered adoption, it's very credible, blah, blah. No, it's not, because you have all those issues, right? So you get a weighted average with 2x2 comparisons, some of which are intuitive and one at least that is not. But if you have multiple groups that are getting treated at different times, there is actually more than one type that is not intuitive. And you have weights that bring us a parameter that is very far away from what we actually want to estimate. So let me just give you a little bit more of an insight into those weights, more of a feel. Okay, so the variation of those dummies simply comes from a Bernoulli distribution. Okay, so that's how the variation of a dummy is computed. The variance of a dummy is computed, and now in what case is the variance maximized? Well, it's maximized when d equals 0.5, and then that product is 0.25. If you can try this yourself, if you have d 0.4, then you get something that's less than 0.25. There's actually here there is a there is some numerical examples. So here's, I mean, you can put in the numbers yourself. That's the weight for the treated versus the untreated groups. But now let's look at the weights for the timing, right? That purely exploit that some units are treated early and some units are treated late. And here the variance in the treatment, there's one parenthesis missing, but is already looking a lot more complicated. Okay? Right, because it's not all units are getting treated or are on the treatment status 1 over the entire sample period. There is some periods where both are treated. There are some where both are untreated. But here we only care about basically the variation in the treatment, which is obviously only there in periods where one is treated and one isn't. And so here, when you just do a numerical example, again, the maximum of variance that you can have is 0.25. These are groups that are treated smack bang in the middle. But then when you have a case, for example, where you have one group treated at, this is just a numerical example to show a case in point, where we basically turned things around and said, well, you know, what gap in the treatment timing gives me a variance that is as big as 0.25? And it turns out it's something like 50% of the sample period. So if I choose the late adopter being treated at 67% of the sample and the early adopter at 15%, or vice versa, 67% of time to go, that's the early adopter, 15% of time to go, that's the late adopter, then I get a variance of 0.25%. But if if the gap in the treatment is a lot lower, they get a low weight, right? So again, in those, so I have many of those 2x2 comparisons, some of which get a huge weight because they happen to be far away from one another. And others get a low weight simply because they're very close to one another. But there is no economic reason why that one group should get a low weight and the other group should get a high weight. That's purely based on the construction of the estimator, and that's something we have to live with. Right? So it's very hard to think then about how an estimator that gives us this, that is based on this weird weighted average, should allow us to recover any policy relevant parameter. Now it can under certain conditions, but it's hard, right? One condition would be that the treatment effects within units across time and across units are the same. Okay, so whoever you treat, it's always just a level shift in the outcome. There is no change in trend due to the treatment. And whether you treat it early or late doesn't matter. If that's the case, then those weights don't matter because your treatment effect is always the same. And we will take a closer look at that in the next video. But if that's not the case, if the treatment effects vary, and we usually have a good reason to believe they do vary, either that units are shifted onto a different trend by the treatment, or that that units differ in how effective the treatment is there, and there is probably a reason why some adopt the treatment earlier than others, because it may simply be more effective in those early adopters, then you have the problem that what your estimator picks up is just some very, very strange weighted average across treatment effects in those different 2x2 groups, and it just gets impossible almost to interpret. Yeah, so these are the lessons so far. The big lesson here is, as in all of econometrics, an estimator is a weighted average, and it's all about understanding the weights. You don't understand the weights, you don't understand what you're doing. Do I always understand all my weights in all my papers? No. I'm not saying, but in an ideal world, you should. And And so here we have strange weights over 2x2 comparisons, some of which are intuitive and obvious and others are less obvious. And the less obvious ones are that, as well as the comparisons between the late adopters versus the early, you also have the opposite case where the early adopters are a control group for the late adopters. And in the next video, we will take a little bit of a closer look and see how that statistical model that I've been talking about in this video actually maps into economically relevant parameters and what assumptions we need to make in order to identify them.